We're in Rosen, Discrete Mathematics and its Applications, Section 2.2 on set operations. We'll cover set operations in this video. Quick aside, we've already discussed, if you're taking the class this video is designed for, Boolean algebras twice, once with propositional logic, and then another type of Boolean algebra using zeros and ones and Boolean sum and Boolean product in chapter 12. Well, set operations fall into a third example of Boolean algebras. And we're going to see that the operators in set theory are analogous to operators in propositional calculus from chapter 1. There'll always be a universal set that we're operating underneath the assumption of, and all sets will be subsets of U as we designate the universal set. All right, the first set operation is called union. If I have two sets A and B, the union of set is denoted A with this upward curving U looking symbol and B. So it's pronounced A union B. And it's defined as the set of X such that X is an element of A or X is an element of B. So there's the analogous propositional logic operation as OR. So you can think of union as OR. A union B, X is an element of A or X is an element of B. We have a Venn diagram here that shows two sets with a little bit of overlapping, set A and set B, and their union would be the boundary that they make with the remainder of the universal set. Here's an example. What is the union of these two sets? 1, 2, 3 union with 3, 4, 5. Well, it'll be the set containing 1, 2, 3, 4, and 5. Intersection. The intersection of A and B is indicated by this downward curving U symbol. And its definition is X is in the intersection of A if X is in A and X is in B. And so the analogous propositional operator to intersection is AND. Think intersection, think AND. Here we have this Venn diagram, and the intersection of A and B is contained where they overlap. So objects in that region are both in A and in B. If the intersection is empty, then it is the two sets are said to be disjoint. What's the intersection of 1, 2, 3, and 3, 4, 5? Well, it's the element they have in common, which is 3. So the set containing 3. Here we have an example of a disjoint set. 1, 2, 3 intersected with 4, 5, 6. The intersection is the empty set. Set complementation. If A is a set, then the complement of A is denoted by this A with a bar over it, and it's the set U minus A. We'll define minus in a little bit, or the difference of U and A. So a complement is X is an element of U such that X is not an element of A. And this not indicated by this not an element of suggests that the logical analogy for complement is negation. And sometimes it's denoted with a little c in the superscript. All right, example, if U is positive integers less than 100, complement of X such that X is greater than 70 will be X such that it is less than or equal to 70. And in the Venn diagram, we see that we have a set A inside of U, and then its complement will be everything in U that is not an A. All right, here's the difference operator. If we have two sets, the difference of A and B, denoted by A minus B, is a set containing the sets of element A that are not in B. All of the preceding operators are commutative. They don't, order doesn't matter, but in this case, order does matter. A minus B is not the same as B minus A. And here's our Venn diagram with A, the elements of A that are not in B. So it's also A minus the intersection of A and B. The complement of B with respect to A rather than with respect to the universal set. So it's X such that X is in A and X is not in B. We can also write it as A intersect B complement, since B complement is everything outside of B in the universal set. The intersection of A with that set will give us the difference. When we're counting up elements in the union of two sets, we have to be careful of double counting. So remember, cardinality is the number of elements in each set. And the cardinality of A union B is the cardinality of A plus the cardinality of B, but we have to subtract out the cardinality of the intersection because otherwise we would double count it. If we wanted to count up the elements in A and B and X was in this intersection, we have to be careful not to double count that X. So if I've got A is a set of math majors, B is a set of computer science majors, we add up the number of math majors to count up all my students, add the number of computer science majors, but we subtract the number of double majors. Otherwise, we will have double counted. And finally, symmetric difference. In this case, we're going to union the two-way difference. So A minus B union with B minus A will be everything that is in the union except for anything that is in the intersection. And that is logically equivalent to and even looks the same as the XOR operator in propositional logic. If an element is in one set but not the other, it is in the symmetric difference. So if I have the universal set, A is 1 through 5, B is 4 through 8, what is the symmetric difference? It'll be 1, 2, 3, and 6, 7, 8 because 4 and 5 are in the intersection. And that is set operations.